All right, let's take a look at a paper that I published recently on nonlinear consolidation theory. This is published in the International Journal of Geomechanics. It appeared in 2016, and it's describing a code that I developed that's a web application written in JavaScript called iConsol.js. And it's an implicit finite difference code for nonlinear consolidation, and it includes secondary compression along with it. And the inclusion of secondary compression is really what makes the paper unique. And so I'd like to walk you through some of the thinking that went into this particular approach to handling secondary compression, which is different from the way that secondary compression is typically handled in a settlement analysis. So traditionally, using programs like Settle 3D by Rock Science, what you would do is say, okay, secondary compression is going to start after some percent consolidation, some average percent consolidation, like maybe 95%. Then you give it a C alpha, and it will add on a straight line in settlement versus log time space that departs from the consolidation curve at 95%. Now that consolidation curve up to 95% did not include any secondary compression. It was based purely on consolidation theory. That's of course not right, because secondary compression is happening continuously. It's happening before a load is applied to the soil, and so it's silly to think that at the time a load is applied on the soil, secondary compression somehow knows that it's supposed to stop and wait until the degree of consolidation reaches 95%, and then pick up and continue on a straight line path. All right, so other people have developed codes that include secondary compression along with primary consolidation. So the formulation I'm adopting is not new. It wasn't my original idea. I'm citing some literature here that deals with it. Consol 97 is a particular example that includes secondary compression simultaneously with primary consolidation. The nice thing about my code is that it's publicly available online, so anybody can run it, and I'll do a demonstration of it as well. Okay, let's come down here and take a look at this figure. I'm going to start over here with part A of the figure, which just shows void ratio versus the log base 10 of time. And this is a pretty typical sort of consolidation curve, right? You see the characteristic shape coming down, and then it goes into a secondary compression region that's clearly evident here between points A and B. Now, by the time we've reached point A, primary consolidation is basically done. All right, we know from Terzaghis 1D theory, it never actually is finished. It takes until an infinite amount of time for primary consolidation to finish. But for practical purposes, we consider it to have been finished actually at a time TP, right? That's the intersection of this projection from the secondary compression part of the curve through this projection of the straight line part of the settlement curve, or the void ratio versus log t curve. All right, now what I'm saying in this figure is what happens if we apply a tiny, tiny little bitty load increment at point A. So we've previously had this big consolidation increment happen. It's done now, and it's going through secondary compression. Then we add just a tiny little increment of load. Well, we haven't really changed the state of the soil by adding such a small amount of load, so it actually just continues along the same path. In fact, let's consider the load increment to just be 0 instead of being tiny. Let's say it's just completely non-existent, 0, but you know, that's what's happening at point A, and we continue along that same path. Well, that's all well and good, except the problem is that we generally restart the clock when we apply a load increment. And typically we assume that secondary compression behavior may not be that influenced by load increment. We know it's different for over-consolidated and normally consolidated soils. So let's say that we did a traditional way and we apply this tiny load increment at point A, and we restart the clock at point A and just plot settlement versus, or void ratio versus time from point A to B. Okay, that's what line B is, or plot B here in the middle is showing. Okay, I've rescaled the void ratio axis, so this is now just tiny zoomed in from point A to B. Now, of course, point A doesn't appear on this plot because this is a log scale on the x-axis. Point A happens at time 0, and you can't plot that in log scale. But what you notice is that this is not a straight line anymore. All right, something that appears to be a straight line in log space on the time axis is not a straight line if you start adjusting the point of reference on that x-axis. All right, so we've transformed what is a straight line into a curved line. That's the exact same data, just plotted differently, right? So instead of having TA be out here at, what is that, like 200 seconds or something like that, now it's 0, right? So all we've done is a horizontal shift of the time axis. Now, if we add back in that horizontal shift and we add in a T star value that's equal to, or we add in the TA value here that was about, I guess it's not 200, it's closer to 300 units here. I don't even have time units on this. But if we add in that initial value, we render this to be a straight line again, right? So this data and this data are identical. The only difference is we've added in a constant to the value we're taking the logarithm of on the time scale. All right, now this poses somewhat of a problem for the traditional method of dealing with secondary compression, because what happens in the field if we apply a pretty small load increment to soil? All right, we're generally going to reset the clock at the time that we apply that load increment, and then we're going to assume that the secondary compression behavior is linear. However, it may not be linear. It may be more like this rather than that. All right, so there's a problem with using time. It turns out that the state of the soil doesn't really know anything about time, right? The state of the soil, I guess, knows its current stress level, it knows its current void ratio, but the soil doesn't know anything about an arbitrary time reference that's in the form of a benchtop clock that's usually set to 0 at the time that a load is applied. Okay, so the formulation that I've adopted here is a little bit of a different idea. It's saying instead of formulating the secondary compression strain rate based on how long it's been since TP happened, which is the traditional approach, we're going to formulate the secondary compression strain rate based on how far we are below a normal consolidation line, or alternatively a reference secondary compression line. The difference between these two will become apparent later on. But let's just say that we're measuring distance down from the normal consolidation line. Well, if you're right on the NCL, secondary compression is fast. As you go through secondary compression and move down, the secondary compression rate slows down. Now, when you're plotting it in log space, it looks like it's a straight line, right? This is a straight line in log space, but actually secondary compression is slowing down with time because we're dealing with a log scale here. So it turns out that it's fairly easy to do some algebra to formulate secondary compression strain rate only in terms of position in E log sigma V prime space. Let me try and find that equation. Here it is, right here. All right, so you can walk through the logic of the equation. This is the typical one here. Well, this is an expression for the void ratio during a secondary compression load stage. And then I'm going through some algebra here to arrive at this equation number 3. So this is the volumetric strain rate due to secondary compression. And it depends on alpha, which is actually just C alpha over the natural logarithm of 10. A T ref value. Okay, so T ref is the time at which you're computing. Well, basically it's like TP if you're using the normal consolidation line as your reference line. So it's a constant. This is not a time variable, it's a time constant. So that's the difference between this approach and the traditional approach, is this one does not depend on a time variable. Okay, and then we just have void ratio, a reference void ratio on the reference consolidation line, C sub C, and then stress and a reference pressure as well. All right, now let's talk about figure 3. So I've gone through the formulation of the secondary compression behavior. Figure 3 shows the problem being solved now using the finite difference solution. We have a clay layer of some height h, initial height, and it's under some initial vertical stress Q naught, and then there's going to be some additional stress increment, delta Q, added to it. The clay is uniform, and I put uniform in quotes here because uniform means that the specific gravity, C sub C, C sub R, and C alpha are all constant. The degree of saturation is assumed to be 1. And then we have either the overconsolidation ratio, the void ratio, or the maximum pass pressure being a constant. Okay, so that's what uniform means. The void ratio may vary if you have constant sigma p prime or a constant OCR. Okay, if OCR is 1, you're going to have looser or softer clay at the top and denser clay at the bottom, right? Because it's in equilibrium for OCR 1. All right, now a common relationship for permeability is that the hydraulic conductivity in log space is linearly proportional to void ratio. So this is the formulation that I've adopted here. Okay, and then the compressibility is just the traditional one. You have the normal consolidation line with a slope of C sub C. Recompression or unload reload line has a slope of C sub R. And then you define that, and of course you can never be on the right side of the normal consolidation line. So the code is capable of handling a condition where you start out over consolidated, then you reach the NCL and move down the NCL during the plastic loading phase or along the C sub C line. All right, now let's come down here. The procedure I'm using to analyze this equation is a finite difference solution scheme. We've spoken about Terzagh's consolidation equation. Terzaghi assumed that C sub V was constant. That means he assumed that permeability and compressibility were constants. That's not true for real soil. Permeability depends on void ratio. Compressibility depends on vertical effective stress and overconsolidation ratio. So it's a little bit more complicated than that. Now, once we start accounting for the fact that permeability and compressibility change, they evolve even during consolidation, the governing differential equation no longer has a closed form solution. So we have to approach this numerically. And the finite difference solution scheme is a numerical strategy for doing that. I won't go through a derivation of all of these equations. This is a fairly equation-heavy paper. Maybe you're interested in that sort of thing and you can read it on your own. But basically, I define a residual expression here that we try and set equal to 0, where we try and minimize numerically for each time step and at each depth. And this is my residual equation. And then I go through some other equations. I'm using a Newton-Raphson iteration scheme, so we have to compute the derivative of the residual with respect to the pore pressure to current depth and time, and then the pore pressure above and below that depth and time as well. So this is just partial derivative expansion to come up with the updated guess of pore pressure using the Newton-Raphson scheme, which is performed here using equation number 15. All right, so I implemented the solution and first compared it with some benchmark solutions that were developed by Pat Fox. So he published a paper showing benchmark solutions using CS2. His solutions are shown here, Fox and Poo, 2015, using symbols, whereas my approximation of his solutions are shown using the solid red line or the dashed blue line. And this is just showing that we get essentially the same solutions. There are some minor differences here for part C, but for the most part, this is showing that the solution is validated. Now you'll notice that the isochrones here are, well, this is void ratio, this is excess pore pressure, but they're often not perfectly symmetric, and that's an outcome of nonlinear consolidation theory. Okay, I also looked at whether this agrees well with Terzaghi's one-dimensional consolidation solution. If we do a really small load increment that basically has constant permeability and constant compressibility, and it agrees really well, right? All these isochrones are pretty much right on, unless we only do something like 20 time increments, in which case you start to get some errors. But for more reasonable number of time steps in the analysis, it's right on. And these small errors are only right at the drainage boundaries. They don't really affect the settlement versus time very much. All right, now one of the outcomes of this particular formulation for secondary compression is that the settlement versus time plot is not unique. Okay, or well, I guess I should say the normalized settlement versus time. So if you plot settlement divided by the ultimate settlement, okay, Terzagh's theory would predict this is a unique relationship. Once you have secondary compression, it's not. And the reason is that it takes a lot longer to consolidate a thick layer than a thin layer. So more secondary compression happens during primary consolidation for that thick layer. So what we're seeing here, this is the black curve is for 0 secondary compression. The blue line is for a 2 centimeter thick specimen that would be kind of like a laboratory specimen thickness. You can see that really there's not much, no noticeable secondary compression happening during primary. It's all happening out here. But once we get thicker and thicker out to 20 meters, now there's a significant amount of secondary compression happening during primary. And we see now after primary you get to this pure secondary compression phase. Notice that the x-axis is normalized by T50. So the purple line is actually taking a lot longer to happen, but because of the normalization, we're able to compare these different curves. So at the end of primary consolidation for the purple line, we get something like 1.7 times the amount of settlement that we would get if we excluded secondary compression that happens during primary. So the key takeaway from this paper is that secondary compression does happen during primary consolidation. In fact, it's constantly happening, always happening for any compressible soil. And failing to consider the simultaneous occurrence of secondary compression with primary consolidation can lead to fairly significant underprediction of settlement versus time. Okay, I'll scroll down a little bit. I just wanted to show that we're also able to reasonably predict settlement versus time for over-consolidated soils. We get primary consolidation happening, and then because of that time resetting problem that I mentioned before, the secondary compression curve line is actually slightly curved. And you see that in some of the data that's been collected by various researchers. This one's from Mesri et al., 97. We've seen it in some other tests as well. Okay, another interesting outcome of this problem is that if the secondary compression is happening faster than water can get through the soil, you end up producing excess pore pressure. Now this may seem counterintuitive, but we actually experimentally verified it. So we took a specimen of peat, consolidated it to some pressure, and then simply closed the drain taps on the triaxial cell and monitored the pore pressure buildup. And pore pressure, sure enough, did increase with time, as shown here with the black data. Now there's a lot of water coming out of the peat, and it filled up the burette, so we had to terminate the solution or the test right there. Okay, so I ran the consolidation code as well by not allowing any excess pore pressure to dissipate through the top and bottom, and you can see that there's really good agreement between the predicted buildup of excess pore pressure and the measured values as shown here. And this is volumetric strain versus time, and then this is pore pressure after we close the drain tap. So we're able to get both pretty accurate here. Okay, well, I think I've covered the predominant features of this paper. There are more equations down here if you're interested in ever implementing this thing, but I have already implemented it and will demonstrate it in a separate video.